Now we come towards some properties related with elastic properties of the body. Elastic properties of the body. So here we will just go through with a stress-strain graph. That is a graph between stress and strain of the body that is shown in the figure. So we are finding strain is taken on the x-axis, stress on y-axis. Stress is force per unit area. Strain is the change in shape. So the various points on the graph represent the different states of the body as discussed below. First is the elastic limit. That is, we go on applying the force on the body and we find that the change in shape is going on to a certain limit, and that is called elastic limit. After elastic limit, if we will go on applying the force, then we will find the body will start yielding. That is, yielding means that is saying that please kindly don't stretch me. So elastic limit means that we go on applying the force to a certain limit, and up to that we will find that extension in length will go on, or extension in dimensions will take place. But beyond that, if we will go on applying the force, we will find that the body will start yielding, and we find that a yield point will come for a specific duration, and after that, if we still go on applying the force, it will break, and that is called the break point. So now the main concept is the limit of stress beyond which the elastic properties of the body come to an end and a stable change is produced in the body. The another thing is that maximum stress which on removing the deforming force makes the body to recover completely its original state. Another thing is in the above graph, point A is elastic limit. Yield point, as I have explained, yield point, that is in the figure, B is representing the yield point, that is between A and B, we are further applying the force and the wire is yielding to stop applying force. But if you go on applying force, then up to position B, the yielding will continue. So elastic limit, that is beyond point B, when the length. So this is what the main concept. And after the elastic limit, beyond the point B, when length of wire begins to increase without applying the force, that limit point is called the yield point, and that is point B. In the above graph, this position is represented by point B. Now, breaking point. Now we find the position when the strain becomes so large that the wire breaks down at last, that is called the break point. At this position, the stress acting in that wire is called breaking stress, and the strain is called the breaking strain. The situation comes after the yield point. The breaking stress also measures the tensile strength. In the graph, this position is indicated by point D. So we can refer to point D, and that is called the break point. And now we come towards elastic relaxation time. That is, this is the duration in which the deformation is going on, and break point. Before break point, the wire slightly relaxes just momentarily and then breaks. Now we come to the main concept. On removing an external force, the body does not recover to its original state instantaneously, that is at once, but it comes to original state after some time. This is called the elastic relaxation time. It is very, very small. This property is found in glass, the quartz, the phosphor, bronze, silver, etc. That is, when they are stretched and we remove the force, they come back to their original position, not immediately, but it takes time, and that time is called the relaxation time. Now, relaxation time is large for glass and it is negligible for quartz, so quartz is more elastic as compared to glass. Elastic fatigue. Fatigue means that is tiredness. That is, wire undergoes tiredness. When an applied force on a body is changed rapidly, several times, it loses elastic property after some time. It is called elastic fatigue. This effect is temporary. the body becomes elastic again after some time. Now we come towards the elastic hysteresis. Now what basically is the elastic hysteresis? So a point will clear it. That is, when a force is applied on the body, the strain produced in the body does not follow the stress and lags behind. So when we apply the force and strain produced in the body does not follow the stress, that is, stress is there, but the body is not following it, and stress is slightly lagging behind the strain. So the lagging of strain from stress is called the elastic hysteresis. Now, next point is the strain produced by increasing the weight and by decreasing the weight are different due to elastic hysteresis. So we'll find that strain produced by increasing weight and by decreasing weight are different. So next point is the substance whose elastic relaxation time is small. Their elastic hysteresis is also small, such as quartz, silver, phosphor, and bronze, but not rubber. So that's why they are more elastic bodies. Elasticity is more. Effect of temperature on the elasticity. When we say effect, then if some heat is applied or if the temperature is changed, then in the elastic body or the body's exhibiting elasticity will have the slight variations lengthwise, the area-wise and volume-wise. Now, as the temperature increases, the elastic property of the material decreases. That is, we are saying elasticity decreases. On decreasing the temperature of a substance, the property of elasticity increases. That is, elasticity will be more. Now, Hooke's law, as I have explained earlier, stress is proportional to strain under the elastic limits. That is what the meaning of Hooke's law. So now we come to the main context. Within elastic limit, the stress is proportional to strain. That is, stress is proportional to strain, or stress is equal to E into strain, and E is equal to stress over strain, and that is what known as the Hooke's law. So E is constant of the material and is called coefficient of elasticity. That is, coefficient of elasticity is stress by strain. So if we change the material, we find that its elasticity will go on changing. Now, coefficient of elasticity depends upon the nature of material. If the nature of material changes, there will be variation in the elasticity. The temperature of the material, because it will make variation lengthwise, the area-wise, or the volume-wise. And the coefficient of elasticity does not depend upon the shape, length, volume, thickness, stress, or strain. Within elastic limit, the graph between the stress and strain is a straight line. The unit of the coefficient of elasticity is the same as that of stress. It will be a straight line. So when stress-strain graph is a straight line, we will say that coefficient of elasticity does not depend upon the variations.